Here to talk to you about semi-automatic unpacking, specifically referring to unpacking of malware, nothing to do with machine guns, but talking about something here on OllyBonE. And to get started, man, there's a lot of hackers out there. And the problem that poses for people like me doing malware, reverse engineering, and antivirus companies is that anybody can take a piece of malware and trivially repack it and evade detection. And a lot of times, in my role, I'll be faced with seeing hackers that I've never seen before, yet I've got to figure out how they work and get to the malware inside and figure out what it does. And I really don't want to spend a whole lot of time playing around with the packer code, because that's not unique to the malware. It's something that's just kind of in the way for me. So I don't want to spend my time, messing around with all these different packers, and a new one being written every week and figuring out how they all work is, getting in the way. So I'd like to be able to do this in a more automatic way. So I wanted to review some of the methods that people are using right now when it comes to automated unpacking. The hard way is you can take this particular packer and you can spend a lot of time looking at it, reverse engineering the packer code, figuring out how it writes, the sections, what kind of decryption or compression that it uses, and how it sets up the import table after it's done. It takes a lot of time. But when you're finished with all that, you can then write your own engine to basically do everything that the unpacking code does, handling all these algorithms and compression methods, and then write a one-time use per version unpacker for packer X. And a lot of people have done this, and I'm not knocking it, but it takes a lot of time and energy to maintain something like this. So it's great that people have done this, but there's just not enough of these unpackers for me to go and say, well, I've got FSG version 133. Does on FSG handle that? I don't have time to keep up with all that either. AV engines, they've got to have some sort of unpacking methodology. They have to know something about these packers. And if they are to go and put code into their AV engine for every single packer that's out there, this engine is going to be huge after a while, and possibly introducing even more bugs and overflows and things like that. So that's the hard way. Another approach that people take sometimes is say, well, instead of learning about the algorithm, why don't I just emulate the CPU, and we'll just let this packing code think that it's running and writing to its memory, but we're just going to virtualize all this. And that is a pretty good approach. A lot of people have taken that approach too. Then you don't have to really deal with the algorithms that they're using in packer. You just have to deal with any kind of idiosyncrasies that cause your emulation engine not to work, and just go and fix those. You've got to put a lot of time and upkeep into this emulation engine. It takes a lot of time to get one off the ground. So a lot of times I see people write some things but then not release the code. It's something that I don't have access to. Maybe the antivirus companies have this internally, or somebody like Peter or Dania has his new packet engine, and people just aren't giving it away for free because it's a lot of work, and that's their right. Then there's the cheating method, and I've done this myself, when I'm in a hurry. Just running the code, putting it into memory on a system that I don't care about, or that's a VMware image that I can re-image later. And then, once it's in memory, just go ahead and dump it right out of memory. And, that's, for all intents and purposes, unpacked, but it's not something we can really use if we want to do an in-depth analysis, because we don't know what that code looked like at the time that it started. We don't have a snapshot of what it was like at that moment in time. So we don't know how the variables that were initialized at the start changed, things are in there that wouldn't be in the actual unpacked code. You don't know where the entry point was necessarily. You can do, in some cases, use some heuristics. If you have various compilers and they all do the entry point kind of the same way, sometimes you can find it that way, but other times if it was coded in assembly, you may not have an entry point that's recognizable, so you're kind of left guessing where that entry point was and where all the code started. And there's ways around that, but it's just not a clean way to go about it. So when I look at all the code that I've unpacked of various packers, notice that they all, well, not all, but a great deal of them have a very similar methodology about how they pack and then unpack the executable that they're dealing with. They'll first analyze the code segment and say, okay, I've got 4 segments in this file. I'm going to compress those in various ways. I'm going to take the import table and I'm going to chop it up, and then I'm going to put a subsection at the end of the file, and that's going to be where the new entry point is, so that the unpacking code can run first, and then when it's done its job and everything's processed, the import table is set back up, then it will jump to what we call the OEP, the original entry point, the point that used to be the entry point before it was packed. So this is kind of just a quick graphic example of how it works. In the unpacked code, you've got just very straightforward. Usually the code section is the first section of the file, and then you'll have other sections, data sections, resource sections, and there's an entry point field in the PE header that points somewhere into that code section, and that's where, as soon as the file is loaded, it'll jump to that execution point to begin. In the packed version, we see that the entry point now points down to a new section that's been appended to the file, and then it's going to run, and somewhere in there it's going to store the OEP. And a lot of times this is intentionally obfuscated, so you can't just read the memory, the decryptor stub, or read the file, the raw bytes, and say, okay, here's where the OEP is stored, so I just need to set a breakpoint there. Sometimes you can. I mean, some packers aren't that sophisticated, but in most cases, packers are making a concerted effort to make this information obscure, because it would be pretty darn easy if you could just say, this is the address to set a breakpoint on, I'm done. So if you use OllyBonE like I do, and you unpack code, you probably sat there and say, gee, if I could just set a breakpoint on that section as a whole, and then stop running when it reached that section, because I know that that's when the code is going to be unpacked, then that would be great. And you can do that already. You can toggle a breakpoint on the memory section, but this is break on access, which means that anything that touches that code will cause a break. The problem with that is that before you actually jump and execute this code, you're going to be reading, possibly, most definitely writing to it. So you're going to do this hundreds of times, thousands of times, depending on how big the code is you're unpacking. So you have to set this breakpoint and reset it again and again and again and again and again. Which turns out to be a really slow process. I mean, even if you automate it, you can use OllyScript or something like that, and automate the section, saying, well, am I running yet? No, I'm just reading. Okay, set the breakpoint again. You can do that, but that's really, really slow. And if you're going to do that, I mean, why not just set a trace point to say, if my execution, my instruction pointer is between this range and this range, then stop executing. And that's a pretty old way of writing code. It goes way back in the day. It's pretty common, and because it's not only tremendously slow, you can also detect in the Packer code itself, it can say, hey, check the CPU instruction count and see how much time it's taken to run the subroutine. And if it's taken way longer than it should have, then there's a chance that some debugger is interacting with me and doing tracing. So it would be great, I thought to myself, and hopefully somebody else out there has thought that to themselves, that if I just had a way to break on execution, not access, just the execution of a memory section without having to do all this tracing, I might be able to do something. So that's what OllyBonE is. OllyBonE stands for break on execute for OllyBonE. So how we did this is to look at the architecture and say, well, is there a possibility that I could set a no execute bit? Well, with the x86, you can't. Now it's been added to CPUs since back in the day, but as it stands, the machines I use just generally don't have this bit. So they did solve this problem in the PAX project. Because if you remember, PAX is designed to stop execution if your code happens to be running in the heap or happens to be running in the stack, then that's a sign that there's been a buffer overflow and something's bad has happened. So PAX already took care of this several years ago. So what we do here is we take the same idea, and instead of talking about protecting the stack and the heap, we're just going to look at protecting just arbitrary pages that we just pick out to target, this is where we want to stop execution at. So I hope everybody's familiar with PAX. I have a passing familiarity. I've never actually run it. Anytime you try to do some sort of memory access, you have to translate, your OS has to translate your virtual address that you're asking for to the actual physical address of the memory, so that we can maintain this gigantic virtual memory space, but we only have a small actual physical memory space, and the operating system figures out how to divvy that up and translate it for you. Because this process of doing these virtual memory translations is kind of time-consuming, the Intel architecture uses what they call look-aside buffers. And so the first time you do one of these virtual to physical address translations, a look-aside buffer will cache that resulting address. So the next time you go and get that page of memory, you already know exactly where it is, and it speeds up things tremendously. Well, the thing that made the PAX project possible is that the x86 uses separate TLBs. One is for data, that they call the DTLB, and one is for instructions. That's the ITLB. And because of that, what we can do is make one read one thing and then use another one in a separate method. Basically, we want to give a certain permission to the stack. We want the operating system to be able to read from that stack. So we go ahead and we let the DTLB cache that entry as is. But if we come around and it tries to do a read to execute the stack, then the ITLB doesn't get cached. It throws up a fault and kills the process. And it marks these pages in memory that it wants to protect by the user supervisor bit of the page table entry bit. So basically, it installs its own page fault handler, and anytime a page fault is thrown because a particular page of memory only has supervisor permissions and we're running from user mode, then the page fault handler figures out whether this is a protected area of the stack, or if it's just another user supervisor set by some other processor in the kernel. So using that bit, we can then mark that page and say, it means more than just user supervisor. It means execute, no execute. So to make this PAX concept work as a packer, we just have to do a few things differently. We're not protecting the stack and the heap. We are looking at a section of memory that's really just defined by the PE loader. And we just find every page that belongs to that section. And then we mark those pages. We flip that PTE bit. And then we install our own page fault handler. And this time, instead of PAX, where it's going to try to protect the operating system's integrity by killing that process, all we're going to do is, from the page fault handler, we're going to jump to the INT1 handler, the single-step break handler. And what this does is, this passes our control from the kernel back to our program being debugged. So essentially, OllyDebug comes back and says, I just got a single-step break, and stops right there. So the way this is implemented in OllyBonE is you've got a OllyDebug plugin that basically just handles the figuring out where the section of memory is, how many pages it has, and then sending I/O controls to a kernel module, which basically then just arbitrarily can assign these user supervisor bits to all these pages, and then also installs its own page fault handler to override the normal page fault handler and redirect the flow when we want to. You could also, if anybody's interested in using IDA for this, you could also do this with the same kernel module. All you need is a IDA plugin, basically, that can figure out where the memory segment that you want to target is, and just set I/O controls for all of those pages. So it wouldn't be hard to implement. I just haven't done it because I typically don't use IDA as a debugger. So we're going to a little bit about the process of how it actually flows in the page fault handler here. So your packer is now trying to unpack itself, and it's attempting to write to this page that we've set to be no execute. So at this point, this is the first time we try to access it, so there's no virtual address translation. So the page table, basically, the walk happens, and it comes back with a user supervisor bit set, so it generates a page fault. So that the kernel directs into the page fault handler, where we've taken over the flow, and we check and see if that page fault belongs to us, if it's something as a result of what we've done here in OllyBonE, or whether it's a real page fault that just needs to be passed on down. So if it does belong to us, what we do is we decide whether or not this is a data or an execution access. And that's pretty easy to do. All we have to do is look at the faulting address, and then say, which is passed to our page fault handler, and then see if that equals the instruction pointer, which we can also get from one of the kernel instructions. So if it doesn't equal the instruction pointer, that means this was a data access. It wasn't trying to execute here, it was just trying to read. So what we do is we'll toggle that PTE bit. We'll set it back to user access. Then we'll do a read from the page. And when we do that, that caches this page table entry. So we don't have to do this again. That is cached into the DTLB, and then it's good. The next time it wants to read, it doesn't have to go to our page fault handler, so we don't slow the system down terribly. Then we, after we've gone ahead and cached that, then we just toggle that page's bit back to supervisor mode, so that when our potential execution happens, that page fault will be hit again. So when that happens, hopefully, this is the target segment that we've guessed is where the execution is going to occur. If it does happen, then what will happen is we have another page fault. The translation capture tried to do a page table walk, and then it came up and said, hey, you only got supervisor bid set here and you're only a user, so it's going to generate that page fault for us. Once again, our page fault handler says, is this us? Does this belong to something else in the system? And then if it belongs to us, it says, does this constitute an execute access, which is now the faulting address equals the instruction pointer address. So when that happens, what we have to do is pop one extra argument off the stack, because the page fault handler is called with an argument that the int1 handler is not. And then we simply jump to that interrupt point handler and let OllyBonE take back control of the program. This works great on standard hardware. It works pretty seamlessly on VMware. I found that Box and QEMU, I've looked at their code, tried to make this work on it, and it just simply doesn't work because they haven't implemented split TLDs. Whenever somebody was writing this part of the code in those projects, they said, well, let's save some time, we'll just put all of the translation look-aside buffers into one table. And so that doesn't give us the ability to do this, unfortunately, on those platforms. I think I filed a bug a while back with QEMU about that. I don't know if it's been fixed since then. It's probably been 6 months since I did that. So it might work at some point. And I have not tested this on Microsoft Virtual PC. I'd be interested to know if any of you use that. I don't use it, so if you do try this out and it does work for you or it doesn't work, I'd like to hear from you. Usage is pretty straightforward. It's actually very fast. You're just going to load in your executable in OllyBonE. You're going to view the memory segment, or the memory map, rather, and look for where your process is loaded, and then figure out, what is going to be that final code segment when it's unpacked. Which piece of those, sections that are loaded in there, which one is going to be the one that's running in the unpacked state. And that's guesswork sometimes. Sometimes you'll know because you're familiar with a particular packer. You don't have to know all the algorithms, but you'll know at least that it's always going to jump to section 1 after it's done. It's pretty typical. Sometimes you'll get it wrong and it'll never break and it will run to completion. So if you're analyzing malware, that can be bad if you're not running this on a protected system that's isolated. If you're not using this for malware, you probably don't have a problem. But basically, there's a REcon execute flag that's been added to the menu, in the right-click menu in the virtual memory space. So we just toggle that, and we run the program. And then hopefully, when it tries to execute that section after it's unpacked, you'll encounter the single-step break. So control goes back to OllyBonE, and then it'll dump you out basically at the OEP. Exactly where you want it to be in one step. So theoretically, that's how it should work in most cases. The differences between packers mean that it doesn't always work quite as cleanly as that, and I'm going to show you actually a video demo of about 5 different packers and using OllyBonE on them. Okay, so the first packer that we're going to attack here is FSG, which is a pretty easy one to manually unpack. If you've ever walked through the code, there's not much to it, and if you've looked at like the 2 or 3 different versions that are out there, you can spot pretty quickly the point at which it's going to jump to the OEP. But it's also a pretty common one that malware authors like to use, so I'll show you how long it takes to do this. Alright, so we loaded it up, and we are landing somewhere in memory, and if we look, this is the memory map, and we can see that the code segment starts at 401,000, and we have actually started at 404,000, so we're actually in that subsection right now. So what we're going to do is we're just going to toggle, right-click and toggle our REcon execute flag for that section. And then we're just going to hit the play button. And down at the bottom there you can see it's already hit our REcon execute. So just run a break code analysis here, and we can now read the strings that are in the file itself. I'd like to thank Computer Banya for providing these packed executables that he uses to test his depacket engine, saving a lot of time and having to go and find a bunch of packers and pack something up with. So that's what we should see every time it's unpacked, basically. So this one's done. We can dump this right now, and we get the OEP, and we're good to go. All right, moving on to a older version of UPack. Once again, we see we're looking at the memory map. We are well out of that initial code section there. We are in the stub section. So we'll set our REcon execute, hit play, and it's already done. Analyze code, and we can read it fairly. So that's 2 fairly straightforward, easy ones. I would have put UPX in here as an example because that's also a very common one. For some reason, UPX did not like Peter's sample executable. It wouldn't compress it. All right, so this is AsProtect or AsProtect. Is it AsProtect or AsProtect? No, AsProtect sounds kind of funny. It sounds a heck of a lot better than AsPack, but well, I never know what the concept is. But we'll look at this one now. This one takes a few more tricks. We can see that we've started this up, and we are, because we've already unpacked this a couple times, we know that that is actually our OEP. So it starts up in that actual code section. So we're not going to be able to simply set a REcon execute right now on that section because we're already there and we wouldn't be able to execute anything. So we're going to have to work around that. And fortunately, we can see here that this push and this call and return, all this is just a jump basically into another section there at 405,001. So we'll just step through that. And now we've landed in another section. So we go back to our memory map. We can set our REcon execute on the code section. Hit play. And wah, wah, wah. There's a debugger detection built into AsProtect, and it detected that we were running this under OllyBonE and didn't like it. So we're going to have to re-strategize here because just being able to unpack this stuff doesn't necessarily mean that it doesn't detect our debugger. So fortunately, this debugger detection technique is being used here is not all that sophisticated. So basically, we could use the isDebugPresent plugin for OllyDebug, and it just hides that isDebugPresent flag in the PEB, so we don't have to show up as being debugged according to the operating system. So we'll go through the motions again. We'll step through that first section, land in the second section, go to our memory map, set our REcon execute, and hit play, and we land somewhere. We land at 40104. A little strange because that isn't, where we know that the OEP is. This code doesn't look like it's been unpacked. So what is it? Well, if we go and remove the kind of messed up analysis that OllyBonE tried to do, we'll be able to read what that instruction is, and it's a return. So what AstroProtect is doing is jumping basically into that code section and returning probably to pop out that address from the stack and jump, and then do something else with it. So what we have to do here in order to continue with our execution is we're going to have to remove our REcon execute that we set. So now we can step and we return. Now we're in the heap even. So we're well out of our code section. So all we have to do now is go back to the memory map, get that section, set a REcon execute one more time, and run the program. And it ends up breaking. Now, we did have REcon execute. We are at the OEP, but the code doesn't look quite right. It's unpacked here. It's just that in certain cases, OllyBonE gets freaked out about the analysis and can't quite get it together. So we are actually at the OEP. We are unpacked here, but running OllyBonE's analysis just looks a little bit wonky here. All right, so that one's unpacked. Let's go on to another one, PE compact. And it does kind of the same trick at the beginning that AstroProtect uses, and that's it's not jumping outside of that code section. It's staying right in that first OEP. So we're going to have to step through it and see what the deal is, and we can see that only a few lines down we get an exception. So what it's doing is it's using the exception handler to do some of the work in packing the code, try to play around maybe with emulators that don't properly handle exceptions. But now that we're in the exception routine, we're outside of that code section. We can set our REcon execute now on that section. We do that and we land here, and that's a jump to another section, which is good news because that means that we're probably getting closer. So we're going to have to remove our REcon execute in order to step, because right now we're just kind of frozen. It won't let us do anything until we untoggle that. And we now just hit F7 to step into that section there. So we just go back to the memory map, set our REcon execute one more time, and run it. And now we land once again at a REcon execute at the OEP. So we're unpacked. And we're still kind of in a condition where OllyBonE just doesn't know what's up with the analysis. But you can see down towards the lower right of the screen, you can see the calls that's making the message box and exit process. So it's unpacked. All right, last one for example purposes here, T-lock. It's also kind of one that uses a few tricks. Starts outside the code section, so it seems like we would be good to go to just go ahead and set a REcon execute. So let's go to our memory map, pick out that target code section and set it. Run the program. Well, we've landed somewhere. What's going on here? Activity outside. Go down and look at, we've got a single step event. And what's happened here is that T-lock is using single step exceptions as part of its unpacking obfuscation. It uses actually a different series of exceptions, and some of those happen to be single steps. So what we're going to have to do here is we're going to have to basically handle the exception, let the program handle the exception, shift F9 or control F9, and just keep running it until we no longer are looking at single step events, but we hit the REcon execute. So that's run through a few of them here. So we just keep on hitting 9, keep playing, handle the exception. And now we've landed somewhere unfamiliar. You can see that there has been a break on execute breached. If we do our analysis, we can see that we're back at the unpack point. I'll rush to download it.
Movie or was that done live?
Sorry?
Was that a video or was that live?
That was a video of me doing it live. The speed of the unpacking was not edited. I just basically put a bunch of clips together. So it's it is a video for most intents and purposes. All right, so yeah, if you want to do that, by the way, exit cap and similar. All right, so the problems we're going to face using this method to unpack malware, we still haven't solved the fact that our debugger can be detected. So any code that we're skipping over when we're setting our REcon execute, it has the potential to do anything that it wants. It detects the debugger, it could just exit, or potentially do other bad things. So you can't really use it as a 100% automated solution. That's why I call it semi-automatic unpacking, because you have to interact with it to some extent. So the anti-debugging stuff, you're still going to need to incorporate that into your debuggers. There's no rule saying you have to use a quote-unquote debugger to use that kernel module. You could write your own unpacking engine and just use that kernel module as the basis for it, and maybe get around some of the anti-debugging tricks. I mean, obviously the isDebug present flag is a pretty trivial one. Some of the anti-debugging tricks I've seen, easy, like they'll just look for a window titled OllyDebug. That's a pretty trivial one. Other ones might be a little harder, where they do like timing of exception handlers. So we have to work on those. Another thing that's kind of frustrating is some of the malware now, or some of the hackers, either or, will refuse to run on VMware. I've had a particular thing that I was struggling with, trying to figure out why I was never able to unpack it, and I thought that something I had done in OllyBonE was wrong, but it turns out that it was actually rejecting the fact that it was running under VMware, and when I ran it under native code, it worked fine. I haven't seen a lot of them. I understand the concept, and I'm pretty sure there are some packers which will be a little less rigid in the way that it unpacks and just puts everything back in nice little sections for you. Some of them will unpack, for instance, to the heap, and then run from there. Just relocate all the jumps and everything, and that's a problem right now because we haven't actually included a method to separate on the heap. I mean, it'd be pretty trivial to do. I just haven't done it to date because figuring out what the heap is and figuring out what potentially shared kernel module code might be is a little bit more time consuming for me. And needless to say, it would be bad if instead of REcon execute, set these permissions onto a piece of shared kernel memory, and every process on the system suddenly came up with one break at the same time. In terms of evasion, I get into a little bit of how you can do it. It's totally possible. I'm not saying this is a end-all method of unpacking. For instance, what if they don't make a stub section? What if they do everything from that initial code section that it's eventually going to jump to? That could happen. You know, we have seen where they start out in the code section, they jump elsewhere. We can always get a little bit finer grained. We can take this protection down page by page. So they may be running in like the last 5 pages of the code section. We can protect the first, you know, how many ever pages up to that point. Once again, it's a little more implementation details, but it's possible. The fact is that you know, OllyBoNE's kernel module is loaded. That can be detected. They could refuse to run, or they might even try to get clever and, you know, use that idle control method to unset the REcon execute after you've set it. Well, the advantage you have here is that I'm giving you the source code to all this, so you could change that naming convention. You don't have to name that OllyBoNE.sys. You can name anything, and you can change the idle control numbers. So if that ever comes around, that's a possibility. I'd be surprised if somebody actually started doing that. One thing that I think might be possible, I haven't really tested it out, if somebody plays around with Virtual Protect and having it read and write the PTEs, I don't necessarily know that the supervisor bit stays intact. So there's a chance that you know, after this memory is touched by some other API call, that we might want to, you know, continually maintain that bit and make sure that it's set, and not just, you know, hit it once and toggle it on and hope that it stays that way. But you can download it right now. GNU GPL. There's still stuff to do on it. I don't know necessarily that I'll implement these changes myself, but since the code's out there, you know, don't complain about it. You can implement it yourself, and then share that back with the community. So there's some ideas there in terms of the REcon execute for shared DLLs. You know, there's some point you might want to be able to set a REcon on the kernel DLL. Theorizing that it's possible by using the copy on write aspects of that page and basically write to that, force it to be copied into another section of memory that's only going to be seen by your process, and then set that REcon execute. So I haven't tested that, just a theory so far, but maybe that will work. But that's all I have for you right at this moment. So, any questions outstanding? Yes?
So your driver is actually modifying the page fault handler from this page fault handler?
Yes. The driver is modifying the page fault handler. It's basically finding the location from the interrupt descriptor payload and is inserting its own. Some of the code in the kernel model is actually adapted from other people's projects. The hooking of that interrupt handler, I actually borrowed some of that code from the Shadow Walker project, if you're familiar with that. It kind of did a similar thing where it took a PAX concept and used that to make it possible to execute, but not possible to read. So that's something that I've done there. But yeah, it's all kind of, yeah, I'm not really a kernel programmer. So, you know, I did put this kernel module together and debugged it and made it work, but I don't consider myself a kernel programmer, or really even a C programmer for that matter. So if you find bugs in there, that's probably why.
You think it'll work in Vista?
I'm sorry, did somebody else?
I'm just wondering, do you think this will work in Vista?
In Vista? I don't know. I'd be interested to find out if somebody's a beta tester. Thank you.